There is something special about humanity's relationship with the coast. For tens of thousands of years, Aboriginal and Torres Strait Islander peoples have maintained deep cultural connections with coastal environments. We are so drawn to these places that today they are the most developed and populated zones in Australia. Ocean environments close to our coasts are not only highly biodiverse, but also provide important sources of protein. Natural habitats like reefs, mangroves and seagrass form protective barriers against inundation and damaging storms. And they are beautiful, remaining an important part of our national identity. But this connection to coasts has come at a cost. Most of the challenges facing our marine environment didn't start in the water. They began on shore. Population growth, urbanisation, coastal catchment development, and climate change are testing the resilience of our coastal habitats. To assess these pressures, we need improved coastal data collection. A multi-scale challenge. Coastal zones are hydrographically and topographically complex across both space and time. As we move from offshore to coastal regions, the issues tend to get finer in scale, from hundreds of kilometres to hundreds of metres. Effective management of our coastal environments requires reliable, long-term and real-time data collection at a range of different scales, from the molecular scale to views from space. At CSIRO, we are developing tools to collect data more efficiently and to integrate them in ways that are meaningful for decision-making. Scale 1, molecular. At the very smallest end of the scale, we are developing our capabilities to monitor changes at the molecular level. Counting fish is difficult. They live in a hidden world beneath the waves, and accessing that world is a costly exercise. Once you're underwater, everything is in perpetual motion, and some species are cryptic and difficult to spot. A common technique has been to record hundreds of hours of video footage and manually identify biodiversity, or use divers to detect species. However, a new method is solving this challenge. Seawater contains eDNA, the genetic remnants of the biodiversity it supports. Reading eDNA means we can identify species living in an area, from plankton to sharks, and monitor in fine detail how they change over time. All this can be done without entering the water. eDNA can help tell us how marine ecosystems respond to climate change effects, such as heat waves. We can use it to detect the presence of harmful species before they take hold, and monitor environmental compliance for marine industries. We can even use this data to assist our understanding of how these systems store or release carbon dioxide, and how these processes might be sensitive to extreme events like floods or tropical cyclones. Scale 2, human. Zooming out from the microscopic, we arrive at the human scale. Accurate modelling requires vast amounts of data. Collecting that data is often challenging considering the remote and volatile nature of the marine environment. Today, we combat these challenges by utilising autonomous and piloted observation technologies, such as sensory buoys and aerial and underwater vehicles. Developments in machine learning mean software can now recognise different marine species and classify corals in live images or videos recorded by autonomous vehicles, leading to more accurate and faster coastal surveys. We are currently using tow camera systems to detect the crown of thorns starfish on the Great Barrier Reef, and using aerial drones and camera networks to monitor sea turtles and dugong in blue carbon habitats. Over time, these autonomous devices can build time-lapse maps of the coastal habitats, allowing us to monitor changes to their condition and health. The advancements in IoT technology have given us the opportunity to deploy more sensors for longer with less need for maintenance. In the future, we may have permanent sensors positioned in critical habitats, keeping watch and providing real-time data. Scale 3, Planetary. Zooming out again, we arrive at the planetary scale. Here we see the big picture. By itself, airborne and satellite Earth observation data is incredibly useful. It supports our marine and coastal monitoring on a broad scale. It underpins modelling and mapping and can help detect the presence of harmful algal blooms or monitor the impact of events like oil spills. It's also very cost-effective. However, the true power of this information is realised when combined with molecular and autonomous data. Together, they create predictive modelling that can enable real-time and future-focused decision-making to support sustainable use of our coastline at multiple scales. Protecting the things we care about. Our connection to the coast will continue for future generations who have the same right as we do to enjoy healthy, functioning coastal environments. With a growing population driving increased development, it is crucial that we continue and expand multi-scale monitoring and mapping. These systems are critical to coastal protection, carbon sequestration, and cultural connection. Utilising safer, less invasive and efficient technology means we can be more strategic in where we spend our limited resources. We can invest effort in protecting coastal environments where it is needed most. At CSIRO, we are working with our partners to integrate multi-scale observations to provide the information that will support decision-making and help maintain healthy coastal systems for the future.